Here is something nobody told you. The most consequential physics experiments happening on Earth right now are not in particle accelerators. They are not in space telescopes. They are in quiet rooms, inside machines that look like expensive wind chimes, running at temperatures the universe has never naturally achieved. And they are producing answers about the beginning of existence, the inside of black holes, and how everything eventually ends. Published, verified, ignored. We have spent a long time with these results, and I want to walk you through all of it, slowly, the way it deserves. Subscribe if you are new to the channel, settle in somewhere cozy, and stay until the end. This one is worth it. Part 1. The coldest place in the universe isn't in space. There is a place on Earth colder than anything nature has managed to produce in the entire observable universe. Not colder than Antarctica, not colder than the dark side of the moon, colder than the Boomerang Nebula, which held the record for the coldest natural object we had ever found, sitting at around 1 Kelvin, 1 degree above absolute zero, a temperature so low that gas expanding outward from a dying star had bled almost every trace of thermal energy into the void. For a long time, that nebula was our benchmark. That was the floor. That was what cold looked like when the universe really committed to it. And then we built something colder in a laboratory in Finland. The device is called a dilution refrigerator. It does not look like something that should matter to cosmology. It looks, if we are being honest, like someone suspended a series of stainless steel cylinders inside one another, connected them with an arrangement of tubes and wires that would confuse a plumber, and then wrap the whole thing in layers of copper-colored thermal shielding that catch the light in a way that makes it look vaguely ceremonial. Companies like Blueforce and Oxford Instruments manufacture them. They are not secret. You can find them in university physics departments, in national laboratories, in the research divisions of technology companies that are quietly spending more money on quantum hardware than most people realize. They sit in climate-controlled rooms, connected to vibration-dampening platforms, surrounded by electromagnetic shielding, humming with a kind of purposeful silence that feels completely out of proportion to what is actually happening inside them. What is happening inside them is this. The temperature is being held at 10 to 15 millikelvin, that is 0.01 Kelvin. The cosmic microwave background, the thermal radiation left over from the Big Bang itself, the ambient temperature of the entire universe, the floor below, which space itself does not naturally fall, sits at 2.725 Kelvin. These refrigerators are running at roughly 270 times colder than the background temperature of the cosmos. You could take one of these machines and place it in the middle of intergalactic space, far from any star, far from any galaxy, floating in the emptiest region we know of, and it would still be radiating heat into its surroundings. It would still be warmer than what is running inside that cylinder right now, in a building somewhere in Colorado or Massachusetts or Bavaria, next to a coffee machine, down the hall from someone's office. The mechanism that achieves this is not intuitive, and it is worth understanding because it tells you something about the lengths we are going to. Our dilution refrigerator uses a mixture of two isotopes of helium-3 and helium-4. At very low temperatures, these two isotopes do something that no other pair of substances does. They spontaneously separate into two phases, like oil and water, even though they are both helium. The helium-3 sits on top, concentrated, and the helium-4 sits below. Now here is where it gets strange. Helium-3 atoms, even at these temperatures, will migrate across the boundary between the two phases. They will dissolve into the helium-4 side, and this crossing requires energy. Specifically, it absorbs heat from the surroundings to happen. Quantum tunneling assists this process at the boundary. The continuous cycling of helium-3 across that phase boundary, driven by a circulation pump, acts as a heat pump running in reverse, pulling thermal energy out of the system at a rate that can sustain temperatures that should not be possible outside of a laboratory. The machine is not fighting nature. It is exploiting a quantum loophole that nature left open, and it is using that loophole to create conditions that the universe itself has never spontaneously produced. Why does this matter? Because at the center of that refrigerator, suspended on delicate mechanical supports, cooled by this cascade of quantum trickery, sits a chip. It is small enough to rest on your thumbnail. It is made of superconducting circuits, usually niobium or aluminum, etched into patterns that would require a microscope to fully appreciate. And that chip is doing something that no human technology has ever done before at this scale. It is maintaining quantum coherence. It is holding quantum state superpositions, entanglements, the fragile probabilistic machinery that governs physics at the subatomic level long enough to perform computations that classical computers cannot, in principle, replicate. The reason the temperature matters so much is almost poetic in its brutality. A quantum state is, at its core, a relationship between possibilities. A qubit, the basic unit of quantum computing, does not store a 1 or a 0. It exists in a superposition of both, weighted by probability amplitudes, and the computation happens through the interference of these amplitudes as the system evolves. The moment any energy from the environment interacts with that system, the moment a stray photon wanders in, or a vibration from a nearby road couples through the shielding, or the temperature rises, even fractionally the quantum state collapses. The superposition resolves. The computation dies. This process is called decoherence, and it is the fundamental engineering problem of quantum computing. Every stray photon is an assassin. Every thermal fluctuation is a contaminant. The only way to hold a quantum state long enough to do something useful with it is to remove almost all energy from reality in the immediate vicinity of the chip. So we built the coldest places in the universe, not because we wanted to, because we had to. In 2025, Fermilab, the particle physics laboratory outside Chicago, the same institution that used to send protons crashing into one another at near light speed in a tunnel underneath the Illinois prairie, inaugurated a dilution refrigerator called Colossus. It occupies 5 cubic meters of volume. It is designed to cool quantum computing hardware at a scale that dwarfs what any single university lab has attempted. Fermilab, an institution whose entire identity was built around making things go faster, is now in the business of making things go colder. That is not a small shift. That is a statement about where physics has decided the next frontier actually is. And here is the thing that deserves a moment of reflection before we go any further into what these machines are doing. The coldest place in the universe is not in space. It is not the remnant of a dead star. It is not the product of cosmic expansion or the slow heat-death gradient of an aging universe. It is a building. It is a machine built by engineers who went to university, who commute to work, who have lunch. And they did not build it to satisfy curiosity, though curiosity played a role. They built it because the computation they needed to run required an environment that nature had never bothered to create. They needed to strip reality down to its quietest possible state, because only in that quiet, only in the near total absence of thermal noise, could they hold the fragile machinery of quantum mechanics still long enough to ask it questions. The questions they are asking are not about engineering. They are not about making a faster computer, or breaking an encryption code, or optimizing a financial portfolio. Some of that is happening in adjacent laboratories, and we will come back to why most of the money flows there and not into what we are about to discuss. But the work that matters most for this story, the work that is quietly rewriting what we thought we could ever know about the universe that work is cosmology. It is physics at the largest scales, studied in a chip at the smallest scales, inside a machine running at a temperature the universe has never naturally achieved. These refrigerators are simulating the Big Bang. They are probing the interior of black holes. They are asking what the vacuum of space is actually made of. They are running models of how the universe ends. And the answers they keep getting back are not nothing. But before we get to what those answers are, we need to talk about the moment everything changed, because it happened recently enough that most people missed it entirely, and understanding it is the only way to appreciate why what comes next is as significant as I think it is. Part 2. December 2024, the line was crossed. Richard Feynman stood up at a conference in 1982 and said something that the physics community wrote down, nodded at, and then mostly filed away for the next 4 decades. He said, if you want to simulate a quantum system, you need a quantum system to do it. This sounds obvious in retrospect. It sounds like the kind of thing that, once stated, you cannot imagine not being true. Of course, a quantum system is the right tool for simulating quantum physics. Of course, a classical computer, a machine that, underneath all its layers of abstraction, is just moving ones and zeros around, according to deterministic rules, is the wrong instrument for capturing the behavior of particles that exist in superpositions, that are entangled across space, that evolve according to probability amplitudes rather than fixed states. Feynman was not being poetic. He was being precise. He was identifying a fundamental mismatch between the tool and the task. The problem is that the tool he was pointing toward did not exist in 1982, and for the next 40 years, it barely existed at all. The history of quantum computing between Feynman's suggestion and the present is a history of incremental, agonizing, technically brilliant progress against a problem that kept finding new ways to be harder than expected. Researchers built qubits out of trapped ions, out of superconducting circuits, out of nitrogen vacancy centers in diamond, out of photons, out of quantum dots. Each approach had advantages and pathologies. Each promised coherence times that real-world noise proceeded to undermine. The qubits kept decohering. The error rates kept climbing. The systems kept collapsing into classical noise before the computation could finish. And then on December 9th, 2024, Google announced the Willow chip. Willow has 105 qubits. That number alone is not the story IBM had crossed 100 qubits in 2022, and more qubits without better performance is just more potential for things to go wrong. The story is what Willow did with those qubits. The story is a number called the logical error rate, and that number came in at 0.143% per cycle. To understand why that matters, you need to understand what has been the central obstacle of quantum computing for the past 20 years. Every physical qubit in a real system makes errors. The environment intrudes. Decoherence happens. A computation that runs for 100 steps in a system with a 1% per step error rate has accumulated so many mistakes by the end that the output is essentially random. The standard theoretical solution to this problem is called quantum error correction. You encode one logical qubit across many physical qubits, use the redundancy to detect and correct errors the way classical computers use checksums, and the logical qubit becomes more reliable than any of its components. This is how ordinary computers work. In a sense, your hard drive uses error correction codes. Your phone uses error correction when it receives a wireless signal. The idea is not exotic. The problem for quantum computers has been this: adding more physical qubits to protect a logical qubit also adds more opportunities for errors to occur. For quantum error correction to actually help, you need the physical error rate to be below a threshold value. Above that threshold, adding more qubits makes things worse. Below it, adding more qubits makes things better, exponentially better. The logical error rate drops. The system becomes more reliable as it scales. Every quantum computing researcher for the past 15 years has been trying to get below that threshold. Willow is below that threshold. The surface code used in Willow, a distance 7 surface code, for those who want the technical term, arranges physical qubits in a grid where neighboring qubits constantly monitor one another for errors, and the errors can be identified and corrected without ever measuring the state of the logical qubit directly. When Google increased the code distance from 3 to 5 to 7, meaning they added more physical qubits per either the logical qubit, the logical error rate dropped each time by a factor of roughly 2 with each step. This was the proof, not a marginal improvement, not a promising trend, a demonstrated, reproducible, consistent improvement in reliability as the system scaled upward. To put this another way, for the first time in the history of quantum computing, adding qubits made the computer work better instead of worse. Google's benchmark claimed that Willow completed a specific computation in under 5 minutes that would take the fastest classical supercomputer 10 to the power of 25 years, deserves some careful handling, because this number gets misquoted and decontextualized constantly. The task in question was a random circuit sampling problem, which is not a task that classical computers are optimized for, and the comparison is to a classical approach that is not using every possible optimization. The claim is real and peer-reviewed, but it should be understood as a demonstration of a specific kind of quantum advantage on a specifically chosen benchmark, not as proof that Willow has replaced classical computing for general purposes. The honest interpretation is more interesting than the hype. Willow proved that quantum error correction works as theorized, that the threshold has been crossed, and that scaling up from here is an engineering problem rather than a fundamental physics problem. That last part is the part that matters. It changes the trajectory completely. It is worth noting that Google is not alone in this space, even though Willow got the headlines. IBM has been advancing its roadmap with Heron and subsequent generations, and its approach to error mitigation, which is somewhat different from full error correction, enabled the experiment we will discuss in detail in a few minutes. Quantinuum has been working with trapped ion qubits, which have different error characteristics. Microsoft announced its Majorana 1 chip in early 2025, claiming a new category of qubit based on topological quantum states that would be inherently more resistant to certain types of errors, though that claim remains under scrutiny from the broader community, and the verification of topological qubits has been a long and complicated story involving at least one retracted paper. The field is moving on multiple fronts simultaneously, but the significance of December 2024 is not just technological, it is conceptual. The moment quantum error correction works, the moment you can reliably maintain logical qubits through long computations, is the moment quantum computers stop being expensive, fragile, error-prone curiosities and start being scientific instruments. And scientific instruments for quantum physics are, by definition, instruments that can probe quantum physics in regimes where no other instrument can go. Feynman's point from 1982 was not just that quantum computers would be useful for chemistry or materials science, though they will be. His deeper point was that the universe is quantum mechanical, and the only machine that can faithfully represent a quantum mechanical system is a quantum mechanical system. A classical computer simulating quantum physics is always making approximations, always truncating, always throwing away degrees of freedom because it does not have enough memory or processing power to keep track of the full quantum state. A quantum computer does not approximate, it evolves. It is, in a very real sense, running the same physics as the system it is modeling. This is the distinction that transforms these machines from calculators into telescopes. Not telescopes pointed outward at light arriving from distant objects. Telescopes pointed inward at the mathematical structure of reality in regions where no photon has ever escaped to carry information back to us. And what they are finding in those regions is the reason we are having this conversation. Part 3. Why you haven't heard about this. Here is something worth sitting with for a moment. The experiments we are about to discuss are not classified. They are not happening in a black site facility funded by an unnamed government program. They are not being suppressed by a physics establishment that has decided the public cannot handle the answers. The papers describing these simulations are published in Nature, in Physical Review D, in ArXiv preprints that anyone with an internet connection can download at no cost. The researchers involved give talks at conferences, post their data, respond to peer review, collaborate internationally. There is no conspiracy here. There is something more mundane, and in some ways more troubling. There is obscurity. The quantum computing research allocation tells part of the story. Finance and optimization applications attract somewhere between 35 and 40% of total quantum research investment. Quantum chemistry and pharmaceutical applications pull in another 30 to 35%. Material science and logistics take up further significant portions. Fundamental physics, the cosmology, the black hole information theory, the vacuum structure experiments accounts for roughly 10 to 15% of the total. The money follows the near-term commercial applications, which is rational, and the coverage follows the money, which is also rational, and the result is that the most scientifically significant work is happening in the least funded and least covered corner of the field. The specific subfield that matters most for this video, lattice gauge theory, which is the mathematical framework used to simulate how quarks and gluons behave, has approximately 500 active researchers worldwide. To put that in perspective, more people work at a single mid-sized hospital than are actively working on the field of physics that directly interfaces with quantum simulation of the early universe. The audience for these papers is genuinely small. When a result is published, the journals that cover it are read by other experts in the same tiny community who cite it and build on it, but it rarely reaches science journalists because the science journalists who could translate it, who have both the quantum computing background and the cosmology background, needed to understand why the result matters are. Rarer still, there is also a visualization problem. The results of a quantum simulation of the early universe do not look dramatic. They do not look like a photograph of a nebula or a gravitational wave signal or a black hole image. They look like graphs. They look like curves on a plot with error bars labeled with equations. The significance is entirely in the mathematics, in the fact that this particular curve matches this particular theoretical prediction that had never been testable before, and that the deviation from the curve in this particular region tells you something about physics that classical computers could never have resolved. If you have not spent years learning the context, the graph looks like nothing, and if it looks like nothing, it does not get covered. Contrast this with the coverage given to quantum computing breakthroughs that threaten encryption, which get front-page treatment because the narrative is immediately legible to anyone. A computer that can break your passwords is a story anyone understands. A computer that can simulate the first microsecond of the universe is a story that requires 15 minutes of setup before the significance lands, and most media outlets have decided that their audience will not sit still for 15 minutes of setup. The result is a widening gap between what physicists know and what the public is told, not because of any deliberate withholding, but because the knowledge is genuinely difficult to communicate, and the infrastructure for communicating it to a mass audience is underdeveloped. The work is public, the implications are profound, and almost none of it makes the news. That gap is exactly what we are here to bridge, because the machines are producing answers consistent, reproducible, peer-reviewed answers from regions of physics that were supposed to be permanently beyond reach. And if you are going to live in a universe where those answers are accumulating, you probably deserve to know what they are. Part 4. The new kind of telescope. For most of the history of astronomy, the fundamental constraint was simple. You could only see what light could show you. This is less limiting than it sounds, because light is extraordinarily informative. Different wavelengths of light carry different kinds of information. Radio waves reveal the structure of hydrogen clouds between galaxies. Infrared light penetrates the dust that obscures star-forming regions. X-rays trace the hottest and most energetic processes in the universe. Gamma rays mark the most violent events, and visible light gives you the beautiful detail that fills the pages of every astronomy textbook. Modern telescopes, from Hubble to James Webb to the Event Horizon Telescope to the Vera Rubin Observatory, are instruments of almost incomprehensible sensitivity, capable of detecting the faint glow of galaxies whose light has been traveling for 13 billion years. But there are regions of the universe from which light cannot escape, and regions from which light has never arrived, and regions so extreme that the physics governing them lies entirely outside anything a photon can report on. These are the 3 forbidden zones for observation. The interior of a black hole from which nothing, not light, not information, not any signal of any kind, can travel outward past the event horizon. The first microsecond after the Big Bang, when the universe was so dense and so hot that it was opaque to its own radiation, a wall of plasma so uniform that no photon could travel more than a tiny distance before being absorbed and re-emitted, which means the oldest light we can ever observe is the cosmic microwave background from 380,000 years after the Big Bang, and everything before that is permanently dark to any telescope. And the vacuum itself, the structure of empty space, the ground state of quantum fields, which does not emit light in any conventional sense and cannot be photographed or imaged, only inferred from indirect effects. These 3 zones represent the most important open questions in physics. What actually happens inside a black hole? What was the universe doing in its first fraction of a second? What is the vacuum made of? And for a long time, the honest answer from physicists was, we have theories, some of them very well supported, but we cannot test them directly. We cannot observe these regions. The questions are real, but the answers are, in a meaningful sense, permanently inaccessible. Quantum computers introduce a third category of investigation that sits between theory and observation. They are not telescopes in the conventional sense. They do not point at the sky and collect photons. But they are also not purely theoretical. They do not just run mathematical calculations that produce predictions, because their results are constrained by actual physics. When a quantum computer simulates a quantum field theory, it is not solving an equation the way a classical computer would by approximating and discretizing and truncating. It is physically instantiating the quantum mechanical evolution of the system. The qubits are not symbols representing particles. They are physical quantum systems, obeying quantum mechanical rules whose collective behavior mirrors the behavior of the system being simulated. The physicist John Archibald Wheeler, who spent decades thinking about the relationship between information and physical reality, argued that at the deepest level, Reality is informational that what we call physical processes are, at bottom, computations. The universe, on this view, is not just described by mathematics. It is mathematics. It is information processing. Wheeler's phrase for this was it from bit, the idea that every physical entity, every particle, every field, every space-time event derives its existence from information theoretic processes. If Wheeler was even approximately right, then a machine that processes information according to quantum mechanical rules is not merely simulating reality, it is, in a limited but real sense, instantiating the same kind of process that reality itself uses. This is a philosophically loaded claim, and we should be careful with it. The quantum computers running today are simulating simplified models, analogues, and approximations of the actual physical systems they are meant to represent. They are not literally recreating the Big Bang or reconstructing an actual black hole interior, but here is the crucial point. Neither is anything else we have. The question is not whether these simulations are perfect replicas of the real systems. The question is whether they can distinguish between theoretical predictions, whether they can tell us which of the competing models of reality is consistent with quantum mechanical behavior and which is not. And on that question, the answer increasingly appears to be yes. So when I say that quantum computers are a new kind of telescope, I mean something precise. They are instruments that can probe the physics of regions that no photon can ever reach by instantiating the relevant quantum mechanical processes in a controlled laboratory environment and measuring the outcomes. The information they return is not an image. It is a measurement, but it is a measurement of something real, something about the mathematical structure of the universe in the regions that have always been off limits. And what that telescope is showing us, when it points at the first microsecond of the universe, is something that physicists are only beginning to fully process. Part 5. The first microsecond, what we could never see. In the beginning, there was plasma. Not fire, not light, not the ordered sweep of galaxies and stars that we see today. In the first microsecond after the Big Bang, and we are talking about 1/1,000,000th of 1 second, a duration so brief that 100 trillion of them would not add up to a single heartbeat, the entire contents of the observable universe occupied a region of space smaller than a grapefruit at a temperature exceeding 2 trillion Kelvin. For comparison, the core of the Sun runs at about 15 million Kelvin, the hottest temperatures we have ever produced in a particle accelerator in the quark-gluon plasma created at the relativistic heavy ion collider at Brookhaven National Laboratory reached a few trillion Kelvin for a Storian-Perst fraction of an instant. The early universe was doing that, but everywhere, all at once, sustained, without a machine to produce it, because the universe itself was the energy. At these temperatures, the fundamental constituents of matter quarks and gluons, the particles that make up protons and neutrons, were not bound together into hadrons. They moved freely through the plasma in a state called quark-gluon plasma, interacting through the strong nuclear force, but not confined into composite particles. The strong force is described by a theory called quantum chromodynamics, or QCD. And QCD is one of the most successful theories in the history of physics. Its predictions have been verified to extraordinary precision, and its mathematical structure is beautiful in the way that only theories that are deeply correct tend to be. The problem is that QCD is almost impossible to compute. The strong nuclear force does not behave like electromagnetism, where the force gets weaker as you move particles farther apart, and perturbation theory works beautifully. QCD is the opposite, it is asymptotically free. meaning that quarks interact very weakly at high energies but are permanently confined at low energies, and the coupling constant that governs the interaction is not small in the regime that matters for understanding how hadrons form. You cannot expand the equations in a power series and keep only the first few terms, because the terms do not decrease fast enough to make the approximation work. QCD at low energies is a strongly interacting, non-perturbative theory, and non-perturbative quantum field theories are, computationally speaking, extremely hard. The standard approach to computing with QCD on a classical computer is called lattice QCD. You discretize space-time onto a grid, put quarks on the sites and gluons on the links, and use Monte Carlo sampling to evaluate the path integral that gives you quantum expectation values. Lattice QCD is a triumph of numerical physics. It has successfully calculated hadron masses, quark masses, the structure of the nucleon, and a range of other properties to high precision. But lattice QCD has a catastrophic failure mode that is directly relevant to simulating the early universe, and it is called the sign problem. The sign problem arises when you try to use Monte Carlo methods to evaluate path integrals at finite baryon density, meaning in situations where there are more quarks than antiquarks, which is exactly the situation the early universe was in. When you have finite baryon density, the integrand in the path integral becomes complex valued. It has a phase, not just a magnitude. When you try to sample this integral using Monte Carlo methods, the positive and negative contributions cancel almost completely, and you need an exponentially large number of samples to resolve the tiny net result. The computational cost scales exponentially with the system size and the baryon density. For the conditions that existed in the first microsecond of the universe, lattice QCD on classical computers is not just impractical, it is, in the limit of interest, impossible. Quantum computers do not have this problem. The reason is fundamental. A quantum computer does not sample the path integral. It evolves the quantum state directly. The time evolution of the quantum field theory is implemented as a unitary operation on the qubits, the same kind of transformation that the real physical system undergoes, and the interference between different paths that causes the sign problem in classical Monte Carlo sampling is exactly the interference that quantum computers handle naturally. The machine is not approximating the integral. It is running the same physics. The simplified model that researchers use to get around the remaining limitations is called the Schwinger model, quantum electrodynamics, in one spatial dimension plus time, with massless fermions. It does not capture all the complexity of QCD. It is a toy model, in the physicist's affectionate sense of the term, but it captures the essential features that make QCD hard for classical computers' confinement, pair production, non-perturbative dynamics, and it can be mapped onto quantum hardware in a way that is computationally tractable with current qubit counts. The Schwinger model is to QCD as a wind tunnel model, airplane, is to a real aircraft, smaller, simpler, but physically equivalent in the properties you care about. And what the quantum simulations of the Schwinger model are showing is that the physics of hadron formation is the process by which quarks and gluons bind together into protons and neutrons in the cooling plasma of the early universe, can be tracked in real time in a quantum system in a way that was previously completely inaccessible. The first microsecond is beginning to open up, not fully, not in the complete complexity of the actual three-dimensional quark-gluon plasma, but the door is open and it is getting wider every year, which brings us to the specific experiment that, more than any other result, made physicists sit up and take notice. Part 6. The IBM simulation that should not be possible. In January 2024, A team of researchers published results from an experiment run on IBM's Heron processor, specifically on the system designated IBM_Torino, that demonstrated something the field had been waiting decades to see. The setup: 112 qubits encoding a 16-site lattice representation of a quantum field theory. The computation required 13,858 2-qubit gates across 14 trotter steps. Those numbers need unpacking because the gap between what they represent and what they sound like is the entire story. A trotter step is the quantum computing implementation of what is called trotterization, a method of breaking up a complex time evolution operator into a sequence of simpler operations. If you want to evolve a quantum system forward in time under a complicated Hamiltonian, a complicated energy operator, you can approximate this by alternating between evolution under different pieces of the Hamiltonian, each piece simpler than the whole. With small enough time steps, this approximation becomes arbitrarily accurate. It is the quantum equivalent of numerical integration. Instead of computing the exact solution to a differential equation, you take many small steps, each one accurate to second order, and the accumulated result is close enough to the truth to be scientifically meaningful. 13,858 2-qubit gates in a single computation is a number that would have been laughable as a target 5 years ago. 2-qubit gates are the most error-prone operations in quantum computing. They require 2 qubits to interact, which creates opportunities for correlated errors that are harder to correct than single-qubit errors. In a system with physical error rates of even a fraction of a percent per gate, 13,000 gates of this type would produce an output buried in noise. The fact that the IBM team got meaningful results from this computation is a testament to the progress in error mitigation techniques, methods like probabilistic error cancellation and zero-noise extrapolation that allow you to characterize the noise in a device and mathematically remove its effects from the output, even when full error correction is not available. What they measured at the end of this computation was the propagation of hadron wave packets. Take a moment to appreciate what that sentence means. A hadron is a composite particle, a proton, a neutron, a pion. Wave packets are localized quantum mechanical states, packets of probability amplitude that move through space according to the wave equations of the theory. What the IBM experiment tracked was the time evolution of these objects, their formation from the underlying quark and gluon fields, their propagation through the lattice, their interactions with one another in a quantum system that was physically instantiating the relevant dynamics. The result was a set of correlation functions, the measurements of how the quantum state at one point in the lattice related to the quantum state at another point as a function of time. When these correlation functions were plotted, they traced out curves, and those curves matched the theoretical predictions. Not approximately, not in the right ballpark, they followed the expected shape of the wave packet propagation with a fidelity that confirmed that the simulation was capturing real physics, not just generating plausible-looking noise. There is a particular moment in this kind of work described by several researchers in subsequent talks and interviews where you run the analysis on the experimental data and you see the theoretical curve emerge from the measurements. It is a moment that physicists who have spent their careers working with purely classical tools, who have studied these theories and computed their predictions in abstraction, do not quite have a context for. The curve is not a prediction being confirmed by looking at a distant object. It is a prediction being confirmed by looking at the output of a machine that, in a physically meaningful sense, ran the same process as the universe ran in its first microsecond. The scale of the computation is also worth dwelling on. The researchers were careful to verify that the circuits they ran on the IBM hardware were beyond the capability of classical simulation, that there was no classical algorithm that could have reproduced the output with comparable accuracy and computational resources. This is important for two reasons. First, it confirms that the quantum advantage is real on this task. Second, it means that the physical results obtained are not just a verification of something we already knew from classical computation. They are new results, accessible only through quantum simulation. The thread running through all of this is the central point. We are simulating regions of reality that are closed to observation. The first microsecond of the universe is not a place a telescope can see. The quark, gluon plasma, the transition to hadron formation, the real-time dynamics of QCD in the conditions that produced all the matter we are made of, these are, from the perspective of direct observation, as inaccessible as the inside of a black hole. But quantum computers can simulate them, and the simulations are working. Part 7. Escaping the sign problem. The sign problem deserves a little more attention because solving it, or rather circumventing it entirely, is one of the most significant things quantum computers bring to fundamental physics. Here is the clearest way to think about it. Classical physics, at its core, follows definite trajectories. A billiard ball rolls from here to there along a path you can calculate. Even stochastic classical systems' random processes, thermal fluctuations, can be sampled efficiently because the probabilities are always positive. Monte Carlo methods work beautifully for these systems. You randomly sample configurations, weight them by their probability, and average to get expectation values. The mathematics is clean, and the computational cost scales reasonably with the system size. Quantum mechanics does not work this way. In quantum mechanics, the correct way to calculate transition amplitudes is through the path integral. You sum over all possible paths between initial and final states, weighted by a complex number called the action. The absolute value of this weight tells you the relative importance of a path, but the complex phase, the angle in the complex plane, determines how the contributions from different paths interfere with one another. It is this interference that produces all the distinctively quantum phenomena: the double-slit interference pattern, quantum tunneling, the energy levels of atoms. The interference is not a complication of the quantum description, it is the physics. The sign problem arises when you try to evaluate the path integral numerically by sampling, because the complex phases mean that different configurations contribute with both positive and negative signs, and they nearly cancel. The sum is small compared to the individual terms. You need to evaluate an enormous number of terms to resolve the small net result. The number of terms you need grows exponentially with the system size. For the early universe, with its finite baryon density, this exponential growth makes the problem computationally intractable regardless of how fast your classical computer is or how clever your sampling algorithm. A quantum computer approaches this problem differently. Instead of sampling the path integral, it directly simulates the time evolution of the quantum state. The state of the system at each moment is encoded in the qubit amplitudes, and the Hamiltonian, the energy operator, drives the evolution forward in time according to the Schrödinger equation. The interference that causes the sign problem in classical Monte Carlo is not a problem at all in this framework, because the quantum computer is not sampling, it is evolving. The machine handles the interference naturally, because it is itself a quantum system in which amplitudes add and interfere as they should. The conceptual shorthand for this is, the machine is the equation, not in a metaphorical sense, but in a fairly literal, physical sense. The time evolution of the qubit state under the programmed Hamiltonian is the same mathematical process, the same physical process, as the time evolution of the quantum field theory being simulated. The quantum computer is not computing what the theory predicts. It is doing the theory. Now, this remains true only within limits that are important to acknowledge. The systems being simulated today are still simplified lower spatial dimensions, reduced particle content, approximations in the Hamiltonian. The full three-dimensional, finite density QCD of the early universe is still beyond the reach of current hardware, but the trajectory is clear and the progress is quantifiable. In 2025, a team at the University of Innsbruck published results from a two-dimensional lattice gauge theory simulation using Quiddit's quantum systems with more than two states. In this case, ions entrapped ion hardware that can occupy three or more energy levels, and the increased information density per physical quantum system allowed them to push the system sizes beyond what would have been possible with conventional qubits. Quiddits are not a universal solution to the hardware challenges, but they represent exactly the kind of creative technical adaptation that characterizes progress in this field. The path from here to full QCD simulation is long. It will require fault-tolerant quantum computers with logical qubit counts far beyond what Willow offers today. But the physics has been demonstrated. The sign problem is escapable. The first microsecond is reachable. And every experiment that successfully simulates another aspect of early universe QCD dynamics is another data point confirming that the machines are producing physically correct results about a region of reality that no telescope has ever or will ever see directly. And this is the thread that connects every experiment we are discussing. The unobservable is becoming simulable. Not all at once, not with perfect fidelity, but systematically, reproducibly, publishably. The answers are accumulating, and they are starting to form a picture. Part Aid. The Higgs field slowed down. There is a moment in the first fraction of a second of the universe distinct from the quark-gluon plasma era, though close to it in time, when the Higgs field did something dramatic. In the very early universe, at energies above the electroweak symmetry breaking scale roughly 100 billion electron volts, which corresponds to temperatures around 1 quadrillion Kelvin, which occurred at times around 100 picoseconds, or 1/10 billionth of a second. After the Big Bang, the Higgs field had no preferred value. It sat at zero or near zero, symmetric under the electroweak gauge transformations that unified the electromagnetic and weak nuclear forces into a single interaction. At these temperatures, particles had no mass in the conventional sense, because mass comes from the coupling to the Higgs field, and the field was not yet locked into its non-zero vacuum expectation value. Then the universe cooled, and the Higgs field underwent what physicists call a phase transition. It broke the electroweak symmetry. It settled into a non-zero value, the vacuum expectation value of about 246 giga-electron volts, and in doing so, it gave mass to the W and Z bosons and, through their coupling to the field, to all the other fundamental particles with mass. This is not a metaphor or a simplification. The Higgs mechanism is the reason anything in the universe has inertia. Without the symmetry-breaking event, no particle would resist acceleration, no atoms would form, no chemistry would be possible, no stars, no planets, no life. The electroweak phase transition is when the universe became capable of being interesting. We cannot observe this transition directly. It happened at temperatures we cannot produce in any accelerator currently built or planned. We detected the Higgs boson at CERN in 2012, which confirmed the field exists, but the detection was a single particle excitation, not a measurement of the phase transition dynamics. The transition itself, the process by which the field acquired its value, the structure of the resulting vacuum, the possibility that it involved bubble nucleation, or a smooth crossover, or first-order dynamics. These are questions that the Large Hadron Collider cannot answer. What a team working with Rydberg atom arrays has been able to do is something that connects to this transition in a physically precise way. A Rydberg atom array is a quantum simulation platform distinct from superconducting qubit hardware. You trap neutral atoms in arrangements using focused laser beams, and you can excite them into high-energy Rydberg states where they interact strongly with their neighbors. By engineering the interaction strengths and driving the system through a quantum phase transition, a sudden change in the ground state of the quantum system as a parameter is tuned, you can realize, in a laboratory on a tabletop, a system that obeys the same universality class of quantum field theory as the Higgs mechanism. The specific experimental result involved an array of approximately 5,000 Rydberg atoms tuned through a phase transition in a way that produced what is called the Higgs mode, an oscillation of the magnitude of the order, parameter around its equilibrium value, analogous to the oscillation of the Higgs field around its vacuum expectation value after symmetry breaking. This mode is notoriously difficult to observe even in condensed matter systems because it is generically unstable and tends to decay into other excitations. The experiment resolved the Higgs mode in the time domain, watching it oscillate, tracking its amplitude and frequency, measuring its decay in a way that had not been achieved before at this scale. The connection to the electroweak phase transition is not that the experiment directly simulates the early universe. It does not, and the researchers did not claim it did. The connection is that the Higgs mode is a universal feature of the class of field theories that includes both the condensed matter systems in these experiments and the Higgs field in the standard model. By studying the dynamics of symmetry breaking in a controllable quantum simulation, physicists are developing tools and physical intuition that apply to the unobservable cosmological transition. The lab is not the universe. But the lab is speaking the same mathematical language as the universe, and some of what it says translates. The deeper implication is the one that keeps surfacing in every domain we discuss. Even the origin of mass, the process that made it possible for matter to exist in the form we know, is now being probed through quantum simulation of systems we cannot directly observe. The unobservable is not a fixed frontier, it is retreating. Part 9. The black hole problem that broke physics. In 1974, Stephen Hawking calculated something that should not have been possible. He showed, using a semi-classical calculation that combined quantum field theory with general relativity in a regime where neither theory was expected to be fully reliable, that black holes are not entirely black. They emit radiation, not through any process happening inside the black hole. Nothing from inside the event horizon can escape, but from the space immediately outside it, where the intense gravitational field interacts with the quantum vacuum in a way that produces a thermal spectrum of radiation. The black hole slowly loses mass by radiating energy, and over an astronomically long time, it eventually evaporates completely. The temperature of this Hawking radiation is inversely proportional to the black hole's mass. Stellar mass black holes are so cold their radiation is undetectable, but small black holes radiate intensely and evaporate quickly. The calculation was a triumph. It unified thermodynamics with quantum mechanics and general relativity in a way that seemed to point toward a deeper theory. Jacob Bekenstein had already shown that black holes have entropy proportional to the area of their event horizon, and Hawking radiation gave that entropy a thermodynamic reality. The black hole had a temperature, it radiated, it obeyed the laws of thermodynamics. And then Hawking himself pointed out the problem. If a black hole evaporates completely into Hawking radiation, what happens to the information that fell into it? When you throw an encyclopedia into a black hole, the information in that encyclopedia, the precise quantum state of every atom, every molecular bond, every bit of ink on every page crosses the event horizon and, according to general relativity, ends up in a region of space-time that becomes causally disconnected from the rest of the universe as the black hole evaporates. When the black hole is gone, where is the information? If it is truly gone, if the final state of Hawking radiation contains no memory of what went in, then quantum mechanics is violated. Quantum mechanics is, at its core, unitary. The time evolution of a quantum state is reversible. Information is never destroyed. It is only scrambled. A process that genuinely erases information is not just physically unusual, it is impossible in a quantum mechanical universe. This is the black hole information paradox. On one side, general relativity, which seems to imply that information can be swallowed and permanently destroyed. On the other side, quantum mechanics, which insists that information must be conserved. Both theories are extraordinarily well tested in their respective domains. Both cannot simultaneously be correct about black holes. One of them, or both of them, is wrong in a regime where they have never been properly tested together, and the resolution of this paradox is expected to be a key feature of whatever the correct theory of quantum gravity turns out to be. Don Page, a physicist who was actually a student of Hawking's, proposed a specific prediction in 1993 that has become the central diagnostic for this paradox. He asked, if quantum mechanics is correct and information is preserved, what should the entropy of the Hawking radiation look like as a function of time? Early in the evaporation, the radiation carries little information. The entanglement entropy of the radiation should increase as more pairs of particles are produced. But at some point, the page time the radiation should know enough about the infalling matter that its entropy should start to decrease as the later radiation purifies the earlier radiation by carrying out the information in scrambled form. The entropy curve should rise, reach a peak at the page time, and then fall back to zero as the black hole completes its evaporation and the radiation is in a pure state. This curve, the page curve, is a precise prediction of what must be true if quantum mechanics is correct, and for 30 years nobody had any way to measure it. Not in the radiation from a real black hole, which we cannot observe at this level of detail, even if we could get close enough. Not in any laboratory system that could replicate the relevant physics. The page curve was a theoretical benchmark with no experimental handle. Until, in 2024, an experiment on IBM's quantum hardware produced a measurement that matched it. Part 10. The wormhole that wasn't and what it taught us. Before we get to the page curve measurement, we need to briefly acknowledge an earlier quantum computing experiment related to black holes that generated enormous controversy and serves as an important lesson about the difference between a genuine scientific result and a misleading headline. In 2022, a collaboration using Google's Sycamore processor published a paper in Nature claiming to have demonstrated wormhole dynamics in a quantum system. The result was framed in ways that suggested they had created a microscopic wormhole, and the press coverage was, to put it gently, not calibrated to the actual physics. The word wormhole was everywhere. The implication was that a real spatial shortcut through space-time had been instantiated on a quantum chip. The actual result was more subtle and more interesting in a technical sense, though less cinematic. What the team had demonstrated was teleportation of quantum information through a specific kind of entangled system, a Sachdev-Yeh-Kitaev model, or SYK model, which is a simplified, many-body quantum system that exhibits certain properties analogous to black hole physics in holographic theories. In the holographic framework, where certain quantum field theories in flat space are dual to gravitational theories in higher dimensional curved space teleportation through a maximally entangled quantum system, is described by the same mathematics as traversal of a wormhole. But this correspondence is a mathematical duality between theoretical descriptions. It is not a claim that a real wormhole existed in the laboratory. The physics community pushed back hard. Several prominent researchers pointed out that the demonstration required only 9 qubits, that the classical simulation of the same system was entirely tractable on a laptop, and that the quantum gravity interpretation was being vastly overstated relative to the evidence. The controversy was productive in that it forced a public discussion about what quantum simulation of quantum gravity actually requires versus what a small qubit demonstration of a related mathematical structure demonstrates. The lesson was clear. Rigor matters, and the connection between quantum simulation and unobservable physics has to be established with care, not with a headline. What the Sycamore experiment did show, correctly interpreted, is that certain quantum phenomena that appear in the theory of black holes scrambling, out-of-time order correlators, teleportation through entanglement, can be instantiated and measured in quantum hardware. The controversy was not about whether these phenomena are real or whether the measurements were technically sound. It was about what they implied about actual gravitational physics, and the honest answer is much less than the framing suggested, but something genuinely interesting about the mathematical structure connecting quantum information and quantum gravity. More rigorous simulations were needed, and they came. Part 11. The page curve measured. The experiment conducted at IBM in 2024 presented at a conference in Marrakesh, which is why it is sometimes called the Marrakesh result, tackled the page curve directly. The theoretical framework being tested was not a simulation of a literal Schwarzschild black hole, the spherically symmetric solution of Einstein's equations that describes the black holes formed by stellar collapse. The hardware is not yet capable of that. Instead, the experiment used the Sachdev-Yekitaev model, the same maximally chaotic quantum system that appeared in the Sycamore controversy, but now used more carefully, with a much more specific and precisely defined measurement goal. The SYK model is relevant to black hole information because it is, in a precise technical sense, the simplest quantum mechanical system that exhibits all the information theoretic properties expected of a black hole. It scrambles information as fast as thermodynamics permits. It is what physicists call a fast scrambler. Its thermal properties match those of black holes in the appropriate limits. And in the holographic correspondence, the ADS, CFT duality, that connects quantum field theories to gravity in higher dimensions, the SYK model is dual to a gravitational theory in near-extremal black holes. It is the most direct quantum simulation target we have for the relevant physics. The experiment worked as follows. A quantum system was prepared in a pure state, encoding quantum information in a way that mimicked infalling matter entering a black hole. The system was then evolved under the SYK Hamiltonian, the dynamics of the strongly interacting maximally chaotic system. As it evolved, Hawking-like radiation was extracted by measuring subsystems of the evolving state and computing their entanglement entropy. The entanglement entropy is the key quantity. For a subsystem of a pure quantum state, entanglement entropy measures how much the subsystem is entangled with the rest of the system, how much information is shared across the partition. If the overall state remains pure and information is preserved, then the entanglement entropy of the radiation subsystem must eventually decrease as the system evolves, because the radiation must become less entangled with the remaining system as it carries more information. This is the page curve: entropy up, peak, entropy down. And that is exactly what the IBM experiment measured. The entanglement entropy of the extracted radiation subsystem rose through the early part of the evolution, reached a peak consistent with the predicted page time, and then turned over and decreased. The shape of the curve matched the theoretical prediction for a unitary, information-preserving quantum evolution. The information was not lost. The page curve appeared. Let me be precise about what this result does and does not establish. It does not prove that real black holes preserve information, because it simulates a model, the SYK system, not a real Schwarzschild black hole. The simulation is of a system that is holographically dual to a simplified gravitational theory in a specific low-dimensional setting. It is not a simulation of the four-dimensional black holes that exist in our universe. The gap between the simplified model and the full physical situation remains significant. What it does establish is that the theoretical mechanisms by which information is expected to be preserved, the scrambling dynamics of the SYK, Hamiltonian, the entanglement structure of the quantum state, the way information is encoded in the correlations of the Hawking-like radiation, are physically realizable in a quantum system, and that their behavior is consistent with the unitarity of quantum mechanics. For the first time, the page curve is not just a theoretical prediction. It has been traced by a measuring device. The physicists who ran this experiment were careful about their claims. The language in the paper is hedged appropriately, with all the caveats about the simplified model and the specific holographic regime. But in conversations at conferences and in interviews, the reaction in the community has been something closer to cautious astonishment. The theory said the curve would look like this. The machine drew the curve. These are the same curve. Information, at least in the model, is preserved. Part 12. What this actually means. The page curve measurement is significant enough to deserve some unpacking of what it implies, not for the simplified model, but for the broader question of what quantum computers are telling us about the structure of reality. The black hole information paradox has been one of the organizing debates of theoretical physics for 50 years. Its resolution is expected to require understanding how quantum mechanics and general relativity are unified, the elusive theory of quantum gravity that has resisted completion since the 1920s. The fact that a quantum simulation has produced a measurement consistent with unitary information preservation is a data point that favors the quantum mechanics side of the debate over the general relativity side. It suggests that, in the class of theories that the SYK model represents, information is not destroyed. The framework that makes this most coherent is the holographic principle, the idea, developed over the past 30 years from work by Gerard Hooft, Leonard Susskind, and most concretely in the ADSES, CFT correspondence formulated by Juan Maldacena in 1997, that the physics of a region of space-time, including gravity, is fully encoded in the quantum physics of the boundary of that region. In this framework, a black hole in the bulk of a gravitational space-time is dual to a highly entangled quantum state on the boundary, and the apparent information loss in the bulk description is an artifact of working with an approximate semi-classical gravity theory rather than the full quantum description. The SYK model is a boundary theory, a quantum mechanical system without gravity, whose dual description involves a gravitational system in the bulk. When we simulate the SYK model on a quantum computer and measure the page curve, we are directly probing the boundary description and finding it consistent with unitarity. The gravitational dual, by the holographic correspondence, must also be unitary. The information that appears to be lost in the bulk semi-classical description must be recovered in the full quantum theory. This is not a proof of holography, and it is not a proof that real black holes in our universe preserve information, but it is a demonstration that the mechanisms predicted by the most complete theoretical framework we have for quantum gravity are physically realizable and measurable. The machines are confirming, in the only regime we can currently access, that the picture points toward information preservation. The scrambling dynamics that make this work, the chaotic spreading of information across all the degrees of freedom of the system, are described by quantities called out-of-time order correlators, or OTOCs. These are correlation functions that involve operators at different times in a non-chronological order, and they have been proposed as the key diagnostic for quantum chaos and information scrambling in black holes. Measuring OTOCs in quantum hardware is now technically feasible, and the measurements are providing direct observational data on the information theoretic properties of strongly interacting quantum systems in ways that were completely impossible before fault-tolerant quantum computing became a realistic prospect. The Lyapunov exponent, the rate at which quantum chaos develops, which sets the timescale for scrambling, and which has a theoretical maximum in quantum mechanics, given by 2 pi times the temperature has been measured in quantum simulations. The SYK model saturates this bound, exactly as black holes are predicted to do. The machine is confirming, measurement by measurement, that the theoretical picture of black holes as maximally chaotic information scramblers is physically consistent. We were never supposed to be able to test any of this. The interior of a black hole is, by definition, causally disconnected from us. The information scrambled in Hawking radiation is hopelessly mixed with the thermal noise of the radiation spectrum. The page time for a stellar mass black hole is longer than the current age of the universe. Everything about this problem seemed to be placed just beyond the reach of any possible measurement, and yet here we are, with a curve on a plot that matches the theory. Part 13. The most violent place in the universe. There is a quantity in theoretical physics called the cosmological constant, and it represents one of the most embarrassing failures of prediction in the history of science. When you apply quantum field theory to empty space, to the vacuum, to the ground state in which no particles are present, you find that the vacuum is not empty. Quantum mechanics requires it. The uncertainty principle forbids a field from simultaneously having a precisely defined value and a precisely defined rate of change, which means that even in the lowest energy state, quantum fields are always fluctuating. These vacuum fluctuations are not a mathematical artifact or a bookkeeping device. They are physically real. The Casimir effect, the measured attractive force between 2 uncharged metal plates placed very close together in a vacuum, is a direct consequence of vacuum fluctuations, and it has been measured to match theoretical predictions to high precision. The problem is energy. Each quantum field contributes a 0-point energy, a ground state energy, to the vacuum, and when you add up the contributions from all the quantum fields in the standard model, integrating up to the energies where we believe the standard model is valid, the result is a vacuum energy density of roughly 10 to the power of 112 joules per cubic meter. This is an almost incomprehensibly large number. It corresponds to the energy equivalent of 10 billion 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 kilograms per cubic meter. Now observe the actual universe. We can measure the vacuum energy density of the universe from the observed expansion rate. The expansion of the universe is accelerating, driven by what we call dark energy, and the energy density of dark energy is about 10 to the power of negative 10 joules per cubic meter. This is a very small number. The ratio between the theoretical prediction and the observed value is 10 to the power of 122. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of physics. It is not a small error. It is not a factor of 2 or 10 or even a million. It is one followed by 122 zeros. The vacuum energy is predicted to be absurdly, catastrophically large, and the observed value is essentially zero in comparison. Some mechanism, some cancellation, some physical process we do not understand is reducing the vacuum energy by a factor of 10 to the 122. We have no idea what that mechanism is. This is called the cosmological constant problem, and it is not just an embarrassment for theoretical physicists. It is a sign that our fundamental understanding of quantum field theory and gravity is profoundly incomplete. We have a theory that describes the vacuum and a universe that has a vacuum, and they disagree by the largest amount any theoretical prediction has ever disagreed with any experimental measurement. The vacuum of space, the nothing that surrounds everything, is the most poorly understood thing in physics, and quantum computers are beginning to probe it. Part 14. The experiment that should make you pause. In 2023, a team of researchers at the University of Innsbruck, working with ultra-cold atoms in an optical lattice, performed an experiment that would have been impossible on classical hardware and that speaks directly to a process intimately connected with the vacuum energy problem, false vacuum decay. The concept of the false vacuum is one of the stranger predictions of quantum field theory. A false vacuum is a metastable state, not the true ground state of the theory, but a local minimum of the potential energy that is separated from the true minimum by an energy barrier. Classical physics would say this state is stable. There is no way to get over the barrier without adding energy. Quantum mechanics says otherwise. Quantum tunneling allows the field to tunnel through the barrier and decay to the true vacuum, producing a bubble of lower energy vacuum that expands at the speed of light, converting the false vacuum around it into true vacuum. This process, vacuum decay through bubble nucleation, is not just a theoretical curiosity, it has direct cosmological implications. If the Higgs field's vacuum is a false vacuum, which we will discuss in more detail shortly, then the universe we inhabit is metastable, and a random quantum fluctuation somewhere in space could nucleate a bubble of true vacuum that expands outward, converting everything it sweeps through into a fundamentally different phase of physics. Everything inside the bubble is not destroyed in any conventional sense. It is simply subjected to a different set of physical laws because the values of the fundamental constants depend on the vacuum state of the Higgs field. Alessandro Zenicini and colleagues in Innsbruck created a one-dimensional system of ultra-cold atoms that was tuned to a regime where a false vacuum exists, a metastable phase of the many-body quantum system separated from the true ground state by a quantum mechanical barrier. They then watched, in real time, as quantum fluctuations in the system spontaneously nucleated bubbles of the true vacuum phase. They tracked the growth and evolution of these bubbles. They measured the nucleation rate. They studied the dynamics of bubble walls expanding through the false vacuum background. This is not a simulation of vacuum decay in the standard model sense. The energies and length scales are completely different, and the specific quantum field theory being realized in the cold atom system is not the Higgs field theory, but it is the same universality class of physics. The bubble nucleation dynamics, the scaling behavior of the expanding bubbles, the dependence of the nucleation rate on the height and width of the energy barrier, these are universal features that are insensitive to the microscopic details of the specific theory. By studying them in a controllable quantum simulation, physicists are developing quantitative tools for understanding vacuum decay that can be applied to the cosmological context. The specific measurement that stands out is the nucleation rate as a function of the barrier parameters. Quantum tunneling nucleation rates are notoriously difficult to calculate analytically in real-time quantum field theory. This is, once again, a problem where the path integral has a sign problem that makes classical Monte Carlo sampling inefficient. The Innsbruck experiment measured the nucleation rate directly by watching how often bubbles formed in the system over a controlled time interval. This is a measurement that no classical computation could have matched at the same system size and parameter regime. The image that stays with you from this experiment, and the researchers themselves used this framing in their paper, is of watching, on a laboratory bench, the same physical process that could, if it happened in the Higgs vacuum, end the universe. Not in the actual Higgs field, not at the actual energy scales, but in a quantum system that obeys the same equations, follows the same dynamics, and realizes the same physics in the same universality class. The process is real. The machine is showing you what it looks like. Part 15. Simulating the end of everything. If false vacuum decay represents one possible end of the universe, a sudden phase transition, propagating outward at the speed of light, the D-Wave experiment from 2023 represents a different kind of cosmological simulation, the study of how these bubbles grow once they form. D-Wave is a different architecture from the superconducting gate-based computers made by Google and IBM. It uses quantum annealing, a process in which the system is slowly evolved from a simple initial state to a complex final state that encodes the solution to an optimization problem. The hardware uses quantum tunneling as a computational resource rather than gate operations. And in 2023, D-Wave's Advantage processor, which at the time housed 5,564 superconducting qubits, making it by far the largest qubit count in any operational quantum system, was used to simulate the growth dynamics of expanding vacuum bubbles. The specific simulation mapped the problem of bubble nucleation and expansion onto the Ising model, a network of interacting spins that is the simplest possible many-body physics model. The Ising model is far from the full quantum field theory of vacuum decay in the Higgs sector, but it captures the key topological features: domains of one phase separated from domains of another phase by domain walls, with the dynamics driven by the energetics of the interface and the bulk. By tuning the Ising interactions, the researchers could explore how the geometry of the expanding bubbles depended on the parameters of the theory, how circular or irregular the bubbles were, how quickly they grew, how they interacted with one another when neighboring nucleation events overlapped. The result that attracted the most attention was the scaling behavior of the bubble domains as a function of system size. In theoretical cosmology, there are predictions for how vacuum bubbles would grow in a cosmological phase transition, how the size distribution of domains would evolve over time, how the scaling exponents would depend on the dimensionality of the transition and the nature of the symmetry being broken. The D-Wave simulation found scaling behavior consistent with these cosmological predictions across a range of system sizes that was not accessible to classical simulation. At 5,000 plus qubits, the D-Wave hardware was operating at a scale where the domain structure showed the same critical scaling that theoretical models predict for cosmological phase transitions. To be precise about the interpretation, the D-Wave simulation is not a direct simulation of the Higgs vacuum. The energy scales, the dimensionality, the specific field content are all different. What the simulation demonstrates is that the scaling behavior of vacuum decay and bubble growth in the same universality class as cosmological phase transitions can be measured in real quantum hardware at scales where classical methods fail. The quantitative agreement with theoretical predictions at those scales is the result. This matters for the cosmological constant problem and for vacuum decay models because the predictions depend on non-perturbative dynamics, exactly the regime where classical computation fails and quantum simulation excels. If we want to understand whether the Higgs vacuum is metastable, and if so, what the decay rate is, and what the internal structure of an expanding true vacuum bubble looks like, these are questions that require the kind of large-scale, non-perturbative quantum simulation that D-Wave is beginning to make accessible. The universe may be ending, slowly and probabilistically, in a bubble that has not yet nucleated. Quantum computers are beginning to study the physics of what that ending looks like, and the fact that the simulations are producing results consistent with theoretical predictions at scales no classical computer can reach is both a validation of the theoretical framework and a demonstration that these questions are tractable, that the answers are not permanently out of reach. Part 16. The metastability problem. The Higgs vacuum metastability is worth dwelling on because it is one of the few topics in fundamental physics that manages to be both technically deep and existentially immediate. The question is simple to state. The Higgs field permeates all of space. Its value in our current universe, its vacuum expectation value, sits at the bottom of a potential energy well, like a ball at rest at the bottom of a bowl. This well represents a stable or metastable state. If it is truly stable, if our vacuum is the global minimum of the Higgs potential, then we are fine. The universe will evolve according to the known laws of physics until heat death or whatever other ending applies. If it is metastable, if our vacuum is a local minimum but not the global minimum, then somewhere in the potential energy landscape there is a deeper well, a true vacuum, and our current vacuum is only stable because there is a barrier separating it from that deeper state. The stability of the Higgs vacuum depends on precise values of the Higgs mass and the top quark mass. Both have been measured with some precision at the Large Hadron Collider. The current best measurements of these parameters place the Higgs vacuum in what physicists call the metastability regime, right on the edge between absolute stability and metastability within the measurement uncertainties. The central values of the measurements suggest the vacuum is metastable, but the uncertainties are large enough that stability cannot be ruled out. The calculation of the stability boundary, the precise curve in the mass parameter space that separates stable from metastable vacua, requires computing the Higgs effective potential at 2-loop and 3-loop order. In perturbation theory, and the results are sensitive to the exact values of the strong coupling constant and the top quark mass at high energies. There are theoretical uncertainties in the computation in addition to the experimental uncertainties in the measured parameters. The upshot is that we do not currently know with certainty whether the vacuum we inhabit is stable or metastable. If it is metastable, the decay timescale is enormous. The quantum tunneling rate through the barrier is exponentially suppressed by the barrier height and width, and the best estimates put the vacuum lifetime at somewhere around 10 to the power of several hundred years, a number so large that it makes the current age of the universe look like a rounding error. The probability of vacuum decay occurring within our observable universe in any given billion-year interval is fantastically small. We are in no danger by any practical measure. But the physics is still profound. A metastable vacuum implies that the laws of physics as we know them, the masses of particles, the strengths of forces, the structure of matter, are contingent on a choice that could, in principle, be different. The true vacuum, if it exists, would have different values for these parameters. Life as we know it would be impossible in the true vacuum, not because the transition is violent though it is. The bubble wall arrives at the speed of light, and there is no warning, but because the physics that allows complex structures to exist depends on the specific values of the fundamental constants that obtain in our current vacuum state. This is the existential content of the metastability problem. We may live in a universe that is, by the standards of a multiverse of possible vacua, a temporary phase, a lucky accident that will eventually on timescales beyond any practical relevance quantum tunnel its way out of existence. Quantum computers are not going to resolve the Higgs vacuum stability question directly. The calculation depends on precision measurements of standard model parameters that require particle accelerators, not quantum chips. But quantum simulation is providing the non-perturbative computational tools that allow theorists to check their perturbative calculations, to explore the bubble nucleation dynamics in analogous systems, and to develop the physical intuition needed to understand what vacuum decay would look like if it happened. The machines are making this a calculable physics problem rather than a philosophical one. Part 17. The Singularity, Problem and Theories being tested. General relativity has a feature that physicists have been arguing about since Einstein first wrote down the equations. When gravity becomes strong enough at the center of a black hole, at the beginning of the Big Bang, the equations break down. The curvature of space-time becomes infinite. The density of matter becomes infinite. The temperature becomes infinite. These infinities are called singularities, and they represent the boundary of the theory, the places where general relativity says, I no longer know what is happening here. The common interpretation, which is almost certainly correct, is that the singularities are not physical infinities, but rather signatures of the incompleteness of general relativity as a theory. At the Planck scale, where quantum gravitational effects become important, at energies around 10 to the power of 19 GeV, and length scales around 10 to the power of minus 35 meters, general relativity is expected to be replaced by a more complete theory that does not produce singularities. We do not know what that theory is. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, and a handful of other approaches have been proposed, and none has yet produced a complete, testable, universally accepted theory of quantum gravity. What quantum computers are beginning to do is simulate the quantum gravitational theories that have been proposed and test their predictions against the kinds of measurements that are now becoming accessible. In the context of loop quantum gravity, the Big Bang singularity is replaced by a big bounce. The universe contracts to a minimum size, bounces, and begins expanding again. The bounce dynamics are governed by quantum geometry, the quantized area, and volume operators of loop quantum gravity, and the resulting cosmological evolution is significantly different from the classical picture. In 2024, simulations using quantum hardware began to probe the dynamics of these quantum geometry models in regimes where classical computation cannot reach the strongly quantum, near-bounce epoch where the geometry of space-time is no longer well approximated by a smooth classical manifold. String theory's approach to the singularity problem is different. It replaces the point-particle framework with extended objects, strings, and branes, and suggests that the apparent singularity is smoothed out at the string scale. The holographic approach, in which the Big Bang is described as a phase transition in a boundary quantum field theory, has been proposed as a way to give a non-singular description of the cosmological initial conditions. These are mathematical proposals, and testing them requires computing quantities in the dual quantum field theories that are beyond the reach of perturbative methods, the same non-perturbative territory that quantum simulation is beginning to open up. The work here is genuinely preliminary. Quantum simulations of quantum gravity models are at an early stage. The system sizes are small, the connection to realistic four-dimensional gravity is indirect, and the specific predictions are often limited to qualitative features rather than precise numerical results. But the trajectory is clear. Each generation of quantum hardware allows slightly larger simulations, which probe slightly deeper into the non-perturbative regime, which tests theoretical predictions that were previously completely inaccessible to experiment. The singularity, like the first microsecond, and the black hole interior, is beginning to retreat from the domain of pure theory. Part 18. Space-time as a computation. There is a philosophical framework that has been gaining traction in theoretical physics over the past decade, partly driven by results in quantum information theory that proposes something radical about the nature of space-time itself. The idea, in its strongest form, is that space-time, the fabric of geometry, the arena in which physics happens, is not a fundamental entity. It is an emergent phenomenon. It arises from a more fundamental description that is purely quantum informational. The geometry of space, the dimensionality of space-time, the smooth manifold structure that general relativity describes these are, on this view, macroscopic features of an underlying quantum system in the same way that temperature and pressure are macroscopic features of an underlying molecular system. The fundamental description does not contain space-time. It contains quantum information. This is not a fringe idea. It is closely related to holography and to ADS CFT, where the geometry of a higher dimensional space-time emerges from the entanglement structure of a lower dimensional quantum field theory. The Ryu-Takayanagi formula, which relates the entanglement entropy of a region in the boundary theory to the area of a minimal surface in the bulk geometry, is one of the most elegant results in theoretical physics in the past 20 years. It says, very precisely, that the geometric area of a surface in spacetime is encoded in the information theoretic entropy of a quantum state. Geometry is information. The simulation of entanglement entropy in quantum hardware, which is exactly what the page curve experiment was doing, is therefore not just a test of black hole physics. It is a probe of the relationship between quantum information and spacetime geometry. When we measure the entanglement entropy of a subsystem of a quantum simulation and find that it follows the predicted curve, we are measuring a quantity that holography tells us is related to the area of a surface in a higher dimensional spacetime. We are probing the geometry of a spacetime that does not exist in any conventional sense. It is the holographic jewel of our quantum system by measuring information theoretic properties of qubits. This may sound abstract to the point of being untethered from reality, and fair enough, but consider what it means concretely. If spacetime emerges from entanglement, then the structure of spacetime, the dimensionality, the curvature, the topology, is determined by the entanglement pattern of the underlying quantum system. Changing the entanglement changes the geometry. Measuring the entanglement measures the geometry. A quantum computer that can prepare, evolve, and measure entangled quantum states is, in the holographic framework, a machine that can explore the geometry of dual spacetimes. This is the most speculative domain we discuss in this video, and it is important to be clear that the connection between quantum simulation results and claims about emergent spacetime is currently at the level of theoretical conjecture supported by specific toy model calculations, not established physics. But it is exactly the kind of conjecture that would have seemed permanently untestable a decade ago, and is now beginning to have experimental handles. The machines are not yet building spacetimes, but they are beginning to speak the language of space-time geometry through the medium of entanglement, and what they are saying is being taken seriously by physicists who have spent their careers on these questions. Part 19. The Deci Shock. In March 2024, a telescope in Arizona quietly released a dataset that made a significant portion of the cosmology community stop what they were doing and reread the numbers. The instrument is called the Dark Energy Spectroscopic Instrument, or DESI, and it is mounted on the 4-meter Mayol telescope at Kitt Peak Observatory, sitting on a mountain in the Sonoran Desert about 50 miles southwest of Tucson. From the outside, it looks like most large observatory telescopes: a dome, a mirror, a mechanical assembly pointed at the sky. What makes DESI unusual is what sits at the focal plane: 5,000 robotic fiber positioners, each one capable of repositioning itself in less than 2 seconds, each one capturing light from a different galaxy simultaneously. In a single night of observing, DESI can measure the spectra of roughly 100,000 galaxies. Over its full survey lifetime, it will map tens of millions. The goal of all this is something called baryon acoustic oscillations, and the name is more intimidating than the concept. In the first few 100,000 years after the Big Bang, the universe was a hot, dense mixture of matter and radiation in which sound waves propagated. These were not sound waves in any ordinary sense. They were pressure waves moving through the primordial plasma at roughly half the speed of light, driven by the competing forces of gravity pulling matter together and radiation pressure pushing it apart. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, an event called recombination, which happened about 380,000 years after the Big Bang, the plasma became transparent, the radiation decoupled, and the sound waves froze in place. They stopped right there, locked into the distribution of matter at that moment. The distance those waves had traveled by the time they froze is called the sound horizon, and it is approximately 490 million light-years. That distance is imprinted in the large-scale distribution of galaxies across the universe. You can see it as a preferred separation between galaxy pairs, a subtle excess of galaxy clustering at that specific scale. It is a ruler, a standard ruler embedded in the structure of the cosmos, the same physical size everywhere and at every epoch, which means that by measuring the apparent size of this feature at different distances, at different points in the history of the universe, you can reconstruct the expansion history directly. You can measure how fast the universe was expanding at different times, and from that you can infer the behavior of whatever is driving that expansion, that whatever is dark energy. And this is where the DESI result becomes interesting. The standard model of cosmology, the lambda CDM model, where lambda stands for the cosmological constant and CDM stands for cold dark matter, assumes that dark energy is exactly that, a cosmological constant, a fixed, unchanging energy density of the vacuum, the same everywhere in space and constant across all of time. It does not evolve, it does not interact, it just sits there, uniform and featureless, pushing the expansion of the universe to accelerate at a steady rate. The physics behind it is deeply mysterious. We cannot calculate the value from first principles, and when we try, we get an answer that is off by a factor of 10 to the power of 122, which is the most embarrassing discrepancy in all of theoretical physics. But at least the behavior is simple. Constant is boring, and boring is predictable. DESI found something that is not boring. At 4.2 standard deviations of statistical significance, which corresponds to a probability of less than 1 in 20,000, that the result is a random fluctuation. The first-year DESI data showed evidence that the dark energy density is not constant. It is changing over time. The equation of state parameter, which physicists call W, is -1 for a pure cosmological constant. DESI measured W varying in a way inconsistent with -1 at this significance level. The dark energy driving the expansion of the universe appears to have been stronger in the past and may be weakening now. It is evolving. It has a history. Let me be precise about what 4.2 sigma means in context, because numbers like this get mishandled constantly. In particle physics, the convention for claiming a discovery is 5 sigma, a probability of less than 1 in 3.5 million of being a statistical fluke. 4.2 sigma does not meet that bar. It is below the threshold for a formal discovery claim, and the DEC team has been appropriately careful about calling it 1. There are systematic uncertainties in a galaxy survey of this scale, calibration errors, modeling assumptions about galaxy clustering, possible biases in the redshift measurements that could in principle produce an apparent deviation from the cosmological constant model without the deviation being real. The result needs to be confirmed by additional data, by DESI's own future releases, and by independent surveys, including the Euclid satellite and the Vera Rubin Observatory's legacy survey of space and time, which are both generating data now. But 4.2 sigma is not nothing. It is a result that serious cosmologists are taking seriously, and the discussion it has generated in the community is not the polite dismissive discussion that greets a marginal result. It is the uncomfortable, excited, slightly worried discussion that greets a result that might be real. Because, if it is real, the implications are large in ways that ripple outward in every direction. A cosmological constant, whatever its value, is at least conceptually compatible with the vacuum energy of quantum field theory. We cannot calculate it correctly, but the framework accommodates it. A time-varying dark energy is a different animal entirely. It is not a constant, it is a field, something dynamic, something that evolves over cosmological time, something that has a value now that was different in the past and may be different again in the future. Several theoretical frameworks have been proposed for such a field. Quintessence models describe a scalar field slowly rolling down a potential energy landscape, its value changing as the universe expands. Quiescence models involve fields with non-standard kinetic terms. Phantom energy models, which are genuinely strange, describe a field whose energy density increases over time as the universe expands, which leads to a future in which the expansion becomes so violent that first galaxy clusters, then galaxies, then solar systems, then planets, then atoms are torn apart by the accelerating expansion itself. This endpoint is called the Big Rip, and it is exactly as dramatic as it sounds. The specific behavior of the DESI signal stronger in the past, possibly weakening now, is more consistent with quintessence-type models than with phantom energy, which is some comfort. But the honest answer is that we do not know which model, if any of the existing ones, correctly describes what DESI is seeing. We do not know the theoretical identity of the field. We do not know its potential energy landscape. We do not know how it couples to other fields or to space-time geometry. We do not know whether it is metastable, whether it could, at some point in the future, undergo a phase transition and change the expansion history of the universe dramatically and suddenly. These are not questions that observational astronomy alone can answer. Measuring the expansion history tells you what dark energy is doing. It does not tell you what dark energy is. For that you need a theoretical framework. And for that framework to make testable predictions, you need to be able to calculate the non-perturbative behavior of quantum fields in curved space-time, the same class of calculation that classical computers cannot handle and that quantum computers are uniquely positioned to address. This is the direct connection between the DESI result and everything else we have been discussing in this video. The vacuum structure of a dynamic dark energy field, its potential energy landscape, the stability of its current value, the possibility of tunneling to a lower energy state falls into exactly the same domain as the Higgs vacuum metastability problem and the false vacuum decay experiments we looked at earlier. The tools being developed to simulate vacuum bubble nucleation and growth, to probe non-perturbative quantum field dynamics, to calculate the behavior of strongly interacting quantum systems in regimes inaccessible to perturbation theory. Those are the tools that will eventually be pointed at the dark energy problem. The DESI result, if it holds up, means that the largest scale dynamics of the universe are governed by something we do not understand, something that is changing in ways we did not anticipate, something whose behavior over the next billions of years depends on physics we cannot yet calculate. The standard picture of a quiet, predictable heat death, the universe slowly cooling to equilibrium over trillions of years, rests on the assumption that dark energy is a cosmological constant. If it is not, then the long-term fate of everything is genuinely back on the table. And the only machines that might eventually tell us which future is coming are the ones running at 10 millikelvin, in quiet buildings, in papers almost nobody reads. The universe is not quite what we thought it was. It turns out it never really was, and the further we look, in every direction, the more that sentence keeps being true. Part 20. The end of the universe is back on the table. For the past 2 decades, cosmology had more or less settled on a conclusion about how the universe ends, and the conclusion was, to be honest, a little anticlimactic. The standard scenario goes like this. Dark energy is a cosmological constant, fixed, unchanging, the same everywhere and at all times. Under its influence, the expansion of the universe continues forever, accelerating gently but relentlessly, pushing galaxies apart until the distances between them become so large that light from one can never reach another. The observable universe shrinks, not because space is collapsing, but because space is expanding faster than light can cross it. One by one, the galaxies we can currently see will redshift beyond detection, their light stretched to nothing by the expansion, until the Milky Way sits alone in an observable universe that contains only itself. Then the stars go out. Not all at once. Over tens of trillions of years, timescales so large that the current age of the universe, 13.8 billion years, looks like the first few seconds of a very long movie. The stars exhaust their fuel. The most massive ones go first, burning bright and fast, and ending in supernovae or black holes. The smaller ones, the red dwarfs, are miserly with their hydrogen and burn for trillions of years, but they burn out too eventually. The last stars flicker out somewhere around 100 trillion years from now, and after that the universe is dark, not metaphorically dark, physically dark, populated by the cold remnants of dead stars, white dwarfs cooling toward black dwarfs, neutron stars spinning down, black holes sitting in the centers of what used to be galaxies. And then the black holes go. Stephen Hawking showed that black holes are not permanent. They evaporate. They emit a faint thermal radiation from their event horizons, Hawking radiation, and over time this process drains their mass until nothing remains. The timescale depends on the mass. A stellar mass black hole takes roughly 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, millions or billions of times more massive, take closer to 10 to the power of 100 years. These are numbers that have essentially no analogy in human experience. 10 to the power of 100 years is not a long time the way 1,000,000,000 years is a long time. It is a duration so extreme that the words we use for large numbers stop feeling adequate. But eventually, even those black holes are gone, and what remains is a universe at thermal equilibrium, maximum entropy, no gradients, no structures, no information processing of any kind. A perfectly uniform, perfectly cold, perfectly still soup of the lowest energy particles the laws of physics permit. No stars, no planets, no complexity. Just an endless, featureless, lukewarm nothing spreading outward forever. This is heat death, and for 20 years it was the consensus answer to the question of how everything ends. Not with a bang, with a whisper that gets quieter and quieter until there is nothing left to make any sound at all. Then DESI released its data, and the ending became uncertain again. The DESI result the 4.2 sigma evidence that dark energy is not a cosmological constant, but something dynamic, something that was stronger in the past and may be weakening now, does not just tweak the heat death scenario. It opens the door to completely different endings, depending on what the dark energy field does next. And the range of possibilities is, to put it plainly, considerably more dramatic than a gradual cooling to stillness. Consider what happens if the dark energy field continues to weaken. If the energy density driving the accelerating expansion decreases over time, the acceleration slows. A universe that is currently expanding faster and faster could, if the dark energy weakens enough, transition to an expansion that is merely coasting, and then slowing, and then stopping. And a universe whose expansion stops is a universe that gravity can eventually reverse. The same gravitational attraction that the accelerating expansion has been winning against for the past several billion years starts winning back. Galaxies that have been flying apart begin, imperceptibly slowly at first, to fall back toward one another. The universe contracts. It heats up as it contracts, the same way a gas heats up when you compress it. Structures that took billions of years to form are destroyed in the compression. Eventually, everything reconverges in a singularity, the Big Crunch, the time reverse of the Big Bang, a moment of infinite density and temperature from which our current understanding of physics offers no further description. Whether the Big Crunch is truly an ending, or whether it leads to some kind of bounce, a new Big Bang emerging from the collapse, as some quantum gravity models suggest, is a question that sits at the intersection of quantum mechanics and general relativity, exactly the intersection where quantum simulation is beginning to have something to say. Now consider the other direction. What if the dark energy does not weaken, but strengthens? There is a class of dark energy models called phantom energy, in which the equation of state parameter is more negative than -1, meaning the energy density of dark energy actually increases as the universe expands. This sounds counterintuitive because it is, in ordinary physics, diluting something, spreading it over a larger volume decreases its density. Phantom energy does the opposite. As space expands, phantom energy becomes denser, and as it becomes denser, it drives the expansion faster. And as the expansion drives faster, phantom energy becomes denser still. It is a runaway process, and it ends in something called the Big Rip. In a Big Rip scenario, the expansion of the universe eventually becomes so violent, so fast, operating on such short-length scales, that it overcomes every other force in nature, one by one. First, the gravitational attraction holding galaxy clusters together is overwhelmed, and the clusters disperse. Then the gravity holding individual galaxies together is overcome, and galaxies dissolve. Then the gravity holding solar systems together. Then the electromagnetic forces holding planets together, tearing them apart into dust. Then the forces holding atoms together. Then In the final fraction of a second before the singularity, the forces holding atomic nuclei together, the universe ends not in stillness but in a violent, total, simultaneous shredding of every structure at every scale, down to the most fundamental particles. The current DESI data is more consistent with a weakening dark energy than with phantom energy, which means the Big Rip is not the favored scenario right now. But the uncertainty is real, and the data is not yet definitive, and the difference between a universe that ends in heat death and a universe that ends in a Big Rip is not a small difference. It is the difference between a quiet fade and a violent dissolution. It matters which one is coming, even if both are unimaginably far away. And then there is the third possibility, which does not fit neatly into either category: the false vacuum decay scenario. If the Higgs vacuum is metastable, if the ground state of the Higgs field in our current universe is a local minimum of the potential energy landscape rather than the global minimum, then somewhere in the universe, at some random moment, a quantum fluctuation could nucleate a bubble of true vacuum. This bubble would expand outward at the speed of light, converting everything it passed through into a region of space with different fundamental constants, different particle masses, different force strengths, a different physics entirely. The bubble wall arrives with no warning, because nothing can travel faster than it to announce its coming. Everything inside the bubble is not destroyed in the conventional sense. It is transformed into something that the laws of physics as we know them cannot describe, because the laws of physics as we know them would no longer apply there. This ending is not captured by any of the standard cosmological models. It is not heat death or collapse. It is replacement, a phase transition of the vacuum itself, propagating outward at the speed of light, rewriting the rules of reality as it goes. Quantum computers are the only tools we have that can address the long-term thermodynamics of these scenarios at the level of physical detail they require. The non-equilibrium quantum statistical mechanics of the late universe, the rate at which quantum and thermal fluctuations drive a metastable vacuum toward decay, the behavior of quantum systems as they approach thermal equilibrium over cosmological timescales, the statistics of the rare large fluctuations that could nucleate vacuum decay, these are non-perturbative calculations in quantum field theory. They are exactly the class of problem where classical computation fails and quantum simulation excels. There is one more prediction worth mentioning, because it is the strangest thing on this entire list. In an eternally expanding de Sitter universe, the far future under heat death quantum and thermal fluctuations never completely stop. They are always happening, at every scale, randomly assembling and disassembling configurations of matter. And given enough time, truly enough time, the kind of time that makes 10 to the power of 100 years look brief, those fluctuations will occasionally, purely by chance, assemble something complex. A rock, a planet, a star, and very, very rarely, something stranger. A fully formed, conscious observer, with a complete set of false memories of a life that never happened, existing for a fraction of a second before dissolving back into the thermal noise. These are called Boltzmann brains. They are a genuine prediction of eternal cosmological models, taken seriously by serious physicists, and they represent one of the most philosophically disorienting implications of the long-term thermodynamics of the universe. Whether they actually occur, and on what timescale, and what their existence would imply about the nature of conscious observation in an eternal universe. These are questions that quantum simulation of non-equilibrium, quantum field theory, is beginning to make tractable. The role of quantum computers here is not to replace the telescopes and accelerators measuring the current state of the universe. It is to take those measurements, the DESI dark energy data, the LHC Higgs mass measurements, the Planck CMB spectrum, and use them as inputs to quantum mechanical models of the vacuum structure and its long-term evolution. The calculations are non-perturbative. The physics is in the regime where classical simulation fails, and the question being asked is the oldest and simplest one there is. How does this end? Part 21. The terrifying part, final convergence. Let us stand back and take the full picture in. We started in a room in Finland, inside a machine colder than anything nature has produced in the 14 billion years since the Big Bang, where a chip smaller than a postage stamp is running computations at 10 millikelvin. We trace the line that was crossed in December 2024, when Google's Willow chip proved that quantum error correction works as theorized, and the era of reliable quantum computation began in earnest. We noted the strange silence around these developments, not suppression, but obscurity, the natural result of a 500-person research community publishing in journals that require years of background to read. And then we looked at what those machines have been computing in the domains where no other instrument can go. In the first microsecond of the universe, IBM's Heron processor ran 13,858 two-qubit gates and watched hadron wave packets form and propagate in a quantum field theory beyond the capability of classical simulation. The physics of quark gluon plasma, the formation of the protons and neutrons we are made of, is no longer exclusively a theoretical prediction. It is a measurement. Inside the mathematics of the black hole information paradox, the SYK Hamiltonian running on quantum hardware traced the page curve, the entropy curve, that must follow a specific shape if quantum mechanics is correct and information is preserved. For the first time, the curve that was supposed to be permanently theoretical is a plot on a figure in a peer-reviewed paper. The measurement says, information is not destroyed. In the vacuum of space, the Innsbruck experiment watched false vacuum bubbles nucleate and grow in a quantum system that obeys the same universality class as the Higgs field. The D-Wave Advantage processor simulated the scaling dynamics of bubble growth at qubit counts no classical system could match. The physics of how the universe might end, how the vacuum might decay, is no longer confined to theoretical calculations. It is being measured in laboratories. And over all of this hangs the DESI result 4.2 sigma evidence that the dark energy driving the expansion of the universe is not a constant, that something is changing on the largest scales, that the standard model of cosmology is incomplete in a way we do not yet understand, in a regime that demands exactly the kind of non-perturbative quantum computation that these machines are learning to provide. Look at what connects all of these domains. The first microsecond is unobservable because the universe was opaque. The black hole interior is unobservable because nothing escapes the event horizon. The vacuum structure is unobservable because it does not emit radiation we can directly detect. The Higgs metastability is unmeasurable because the relevant dynamics occur at energies and timescales beyond any direct experiment. And the long-term fate of the universe is inaccessible because the relevant physics requires evolution over timescales longer than the current age of the cosmos. These are the 5 permanently forbidden regions of physical knowledge, the places we were told, by the structure of physics itself, that we could never reach. Not because the technology was not good enough, not because the experiments were too expensive, because the information was causally or energetically or temporally locked away from any possible observation. And quantum computers are returning answers from all 5 of them. Not perfect answers, not the complete physics of the real systems in their full complexity. The simulations are still simplified lower-dimensional analogues, toy models, leading-order approximations to the full theory. the gap between what the machines can currently do and what would be needed for definitive, unambiguous answers about real black holes or the real Higgs vacuum is still significant. Anyone who tells you otherwise is overstating the current results. But here is the thing. The gap is narrowing. It has been narrowing consistently, year by year, as qubit counts increase and error rates decrease, and error correction protocols are refined, and new simulation algorithms are developed. The trajectory from the first quantum computers in the 1990s to Willow in 2024 was not smooth or predictable in detail, but the direction was always the same. The machines got better, the errors got smaller, the computations got longer, and each increment of progress opened a slightly larger window into the physics of regions that were supposed to be permanently dark. The Willow result in December 2024 was a threshold, not a destination. It was the moment quantum error correction was proven to work in practice, which means the engineering of larger, more reliable, fault-tolerant quantum computers is now a matter of resources and time rather than fundamental physics. The roadmaps from Google, IBM, Microsoft, and others envision thousands of logical qubits within this decade and millions of physical qubits within the next. Each doubling of logical qubit count opens a substantially larger domain of non-perturbative physics to simulation. Each improvement in error rates extends the depth of circuits that can be run. The simulations will grow, and as they grow, the answers will get more specific. The questions will sharpen from, is the page curve consistent with unitarity in this simplified model, to, what is the information content of the Hawking radiation spectrum in a more realistic gravitational model? From, does bubble nucleation in this universality class show the predicted scaling? To, what is the nucleation rate of false vacuum decay in the Higgs potential given these measured parameters? From, can we simulate the first microsecond in a one-dimensional model? To, what does the quark-gluon plasma in 3 dimensions tell us about baryon asymmetry? The physicists running these experiments are not speaking dramatically about what they are finding. They are precise and hedged and careful, as good scientists always are, and they are appropriately cautious about overclaiming. But in the conversations that happen after the papers are published, in the conference sessions and the hallway discussions, and the informal exchanges between people who have spent their careers on these problems, there is something that sounds less like caution and more like quiet recognition. The machines are confirming the theoretical pictures. The simplified models are returning results consistent with what we would expect if the full theories are correct. The curve keeps matching the prediction. We were not supposed to be able to test any of this. We were supposed to accept, as a fundamental epistemic constraint, that the beginning of the universe is dark, that the inside of a black hole is unknowable, that the vacuum is opaque, and that the end of the cosmos is too far away to reach. We were supposed to have theories without tests, models without measurements, predictions without experiments. Physics was supposed to reach its edge at these 5 frontiers and stop. It is not stopping. The dilution refrigerators are running at 10 millikelvin. The error rates are falling below threshold. The simulations are getting longer, the systems larger, the physics deeper, and the answers that keep coming back from regions we were never supposed to reach through a mechanism we only fully understood how to build in the last few years, reported in papers that almost nobody reads because the math is hard and the consequences take 15 minutes to explain. Those answers are consistent with a universe in which information is preserved, in which matter formed from a quark-gluon plasma in the first microsecond, in which the vacuum is structured in a way that matches our best theories, in which the physics of ending is as strange and specific as the physics of beginning. The machines are not omniscient. They are not delivering the final theory of everything. They are small and cold and fragile, and they make errors that require extraordinary ingenuity to manage. But they are returning answers from inside the event horizon, and from before the first photon, and from the ground state of space itself, and from the far future of the cosmos, answers that were supposed to be permanently locked away from human knowledge. And that is what is genuinely terrifying, if you think about it long enough. Not the answers themselves, though some of them carry existential weight. Not the possibility of vacuum decay, or the evidence for the page curve, or the behavior of the first microsecond. What is terrifying is the epistemological fact. We built something that can reach into the permanently forbidden and come back with information. We closed the loop on questions that physics had declared, by the structure of the theory, to be permanently open. We made the untestable testable, the unmeasurable measurable, the unknowable known, and the machines, running in their cold, quiet buildings, keep returning answers from places we were never supposed to see.